Okay, the talk I'm going to talk about was published in these two papers, and the first author is Hiroshi Hayashi, who graduated already. So I'm giving talk. Collaborators Tatsumasa Itahashi, who has also graduated, and also Leonid Vlasenko and Marina Vlasenko from Yofei Physical Technical Institute in Russia. And today is October 9, 2009. So we proposed in 2005 the so-called all-silicon quantum computation scheme, where we use silicon-29 nuclear spins as qubits. And then at the end of this linear chain of silicon-29 nuclear spin qubits, there is a phosphorus donor attached to it. And we want to, at the very beginning of the quantum computation, we want to orient these nuclear spins to the same direction, same orientations. And for this, we propose to use phosphorus attached at the end. So we will use phosphorus to orient these 29 nuclear spins. And before we go into the detailed discussions, let me define a few things. First, nuclear spin up is defined as direction of the externally applied magnetic field. Down is opposite direction. And here the magnetic quantum numbers are given for up and down direction. And also this value is important, polarization. Polarization is the amount of nuclear spins or electron spins that are polarized. So here it is total number of spins in the system, up plus down. And up there in the denominator or numerator, that is the difference between down spin and up spin. Okay? So when there is an equal number of up and down, the polarization is 0. But then if you have only up spin, then nuclear polarization is 100%. So that's the definition of the polarization, and let me go on. But before I move on, that's right, I need to emphasize that at thermal equilibrium, for example, at 4.2 Kelvin or so at low temperature, and with some, magnetic field like 5 Tesla or so, the nuclear polarization is only 0.001%. So very little amount of nuclear spins are polarized. And we want to increase that. So as I mentioned, we want to use phosphorus to orient 29 nuclear spins situating around phosphorus. Phosphorus is the donor in silicon at low temperature. It has one nuclear spin and one electron bound to phosphorus. So the blue shows electron cloud, and there's one electron within this electron cloud. Okay? And then we want to use these electron spin bound to phosphorus to orient 29 nuclear spins. So we want to use electron spin to orient 29 nuclear spins. Once 29 nuclear spins are oriented, the nuclear spin diffuse away. So these oriented 29 nuclear spins diffuse out of phosphorus, diffuse away from phosphorus to orient 29 silicon and the whole crystal. So I've already described the motivation, and now the purpose is to understand the property of dynamic nuclear polarization with so-called isotopically controlled silicon. So let me describe the basic mechanism of dynamic nuclear polarization. Here I show ket. The left arrow shows the spin direction of the electron bound to phosphorus. The right arrow shows 129 nuclear spin situating around phosphorus, and whether it's up or down. So it's an electron spin, 29 nuclear spin. Okay? There are two mechanisms. One is known as the Overhauser effect. Here, because we have phosphorus electron spin and 29 nuclear spin, we have combination of two spins leading to 4 different states. Down, up, down, down, up, down, and up, up. And these are electron spin excited states. These are electron spin ground states. So if we shine microwave corresponding to the red transition, of course this is in certain magnetic field, that's why there's a splitting between electrons down and up. And then if we irradiate certain irradiation, we excite electron from the down state to the up states. And then if we keep doing this, sometimes some population of here is transferred preferentially to the population here. And then because we are continuously shining light, we send more population up to this state. At the end of this process, you can see that we have more populations on the left than on the right. More population on the left means more nuclear spin up states. So this way we can realize preferentially 29 silicon having up states more than down states. Okay? So this is so-called Overhauser effect. And this effect occurs exactly at the resonance, so at this shining of this frequency. The other mechanism is known as the solid effect. It's the same diagram, but now we shine microwave corresponding to diagonal excitation. It's either here or either this one. Okay? Overhauser effect, we shine here, but now we shine, for example, flip-flip transition, energy corresponding to the difference between this state and this state. And when we do this, for example, when we, for example, shine energy corresponding to flip-flop transition, energy between this and this one, we send more population to this state, and then this state relaxes to this state. So at the end, we have more population on the right than on the left. This way, we have more down nuclear spins than up nuclear spins. We can do the opposite. We can hit flip-flip transitions and send more populations to the left than to the right. And by doing so, by choosing either this transition or this transition, we can either orient nuclear spins to the down state preferentially or, up states preferentially or down states preferentially. Once we orient 29 nuclear spins, we can perform solid state NMR, nuclear magnetic resonance, to see how much 29 nuclear spins are up or down. So that can be measured by nuclear magnetic resonance. And sometimes for flip-flip transition, we have negative nuclear polarization. For flip-flop transition here, we have positive nuclear polarization as defined here. Okay? So once we orient 29 nuclear spins around phosphorus, those nuclear spins diffuse out by nuclear flip-flop or nuclear dipolar coupling. And schematically, the nuclear spin diffusion looks like this. And those oriented nuclear spins around phosphorus diffuse out of phosphorus and orient all these 29 nuclear spins to the same direction. Okay? So there are two processes. One is generation of polarization around phosphorus. The other is nuclear spin diffusions. And we want to study both, how efficient generation is and how efficient nuclear spin diffusion is. Okay? So now results and discussion. Hiroshi has prepared 7 samples. Here's a sample name. Here's a 29 silicon concentration. It's a bulk crystal. It's a growth method and concentration of phosphorus in the sample. And here's a picture of each sample with a ruler in millimeter. One series sample indicated by yellow, this series is made of natural silicon. So it contains about 5% of 29 silicon. I said about because exactly it has 4.7% of 29 silicon nuclear spins. The other set of sample, for example, indicated by yellow, it has about the same concentration of phosphorus, about 5 times 10 to the 14, or 0.5 times 10 to the 15 per cubic centimeter, but different 29 silicon concentrations. 29 silicon concentration 1.2% to 99.2%. So this is almost 100% 29 silicon crystal. Okay? And we would like to study both the phosphorus concentration dependencies and also 29 silicon concentration dependencies of how well we can orient 29 silicon and how fast they diffuse away. Okay? Experimental method. First, we have to excite electron from down to up states using electron paramagnetic resonance machine, or EPR. Okay? So here's a typical electron paramagnetic resonance signal obtained from phosphorus in silicon. It has two resonances separated by this hyperfine interaction. Then what we do is we sit at one particular magnetic field in an EPR machine, and then we keep sending microwave. So that means, we keep sending electron to a certain level, and we wait for 29 silicon to orient. We just wait. Okay? Sometimes we wait 4 hours. Sometimes we wait 11 hours. Sometimes we wait 24 hours in EPR machine. Okay? It's a long process. So waiting certain time allows 29 nuclear spins to orient themselves to a certain direction. And then once waiting is completed, we take the sample out of EPR machine, out of cryostat, and transfer to the pulse NMR machine nearby, set the sample in NMR equipment. The measurement is performed at room temperature, and see how strong 29 NMR signal is obtained. So this signal tells us how much 29 nuclear spin orientation or polarization is achieved as a result of this process. Okay? And the 29 silicon nuclear spin signal intensity changes as a function of the time. And time here is 4-hour irradiation EPR. 11-hour irradiation EPR. And then measurement at NMR. Just quick measurement. 17 hours saturation EPR. And you can see the longer we wait, more 29 nuclear polarization is achieved. And this polarization growth, intensity growth, is exponential. Okay, so to achieve high polarization, it shows that you have to wait many hours in EPR machine. So Hiroshi performed measurements, perform measurements over and over and over, as you can see. Here, it's the same measurements for 1% 29 silicon sample. Orange is 5% silicon 29 sample. Purple here is 10%, and green is 100%, and so on. Each point, he waited, for example, 34 hours at this particular point, 34 hours in EPR machine, transferred to NMR, and measured. So this is a lot of time that he spent in the lab. And he can measure all these, how 29 silicon orientation grows as a function of the time. Okay? And this also shows the same thing. So this growth is known as a T1, relaxation time for nuclear spins. So he can actually achieve idea of how 29 silicon dynamically behave as a function of the electron excitation. So here, this is just a summary of results Hiroshi obtained. It's a complicated figure, so I'm going to explain step by step. This is 29 silicon 1% sample. This is 5% sample with 10 to the 15 phosphorus. This is again natural silicon, 5% 29 with 10 to the 17, 2 orders of magnitude more phosphorus than this one. Okay? And then we have 10%, 50%, 100% 29 silicon. All measurements were performed at 12 Kelvin except for this one, 3 Kelvin. The solid curve in each plot is a electron paramagnetic resonance curve. So solid curve, and of course the horizontal axis is the magnetic field, and we took 0 as the center of the EPR transition. Okay, magnetic field. Here, the X-band EPR spectrometer is used. So it's about 10 gigahertz of irradiation. Now, each plot, the circles, is the results of NMR, 29 silicon NMR intensity. Okay, 29 silicon NMR intensity. So this plot, particular point means Hiroshi put sample into EPR machine and set the EPR machine at this particular magnetic field, waited for certain hours, and then take the sample out, measure NMR, and found that NMR intensity is this. Okay? Then this point again, he put sample in an electron paramagnetic resonance machine, waited for some time at this magnetic field, and then took the sample out and measured in the NMR machine to find 29 NMR peak having intensity shown here. So the black is the NMR peak intensity. Blue is the EPR resonance spectrum. And they show nice correlation always. Always. So clearly, electron spin resonance is related to how 29 silicon nuclear spins are oriented. Okay? This particular peak has completely different EPR and NMR magnetic field dependencies because it has a very different mechanism. To give you the answer, this is due to Overhauser effect, and the rest are due to solid effect. I show you that there are 2 mechanisms. So let me start with 2 samples, results of 2 samples. One with 29 silicon concentration, only 1%. The other with 29 silicon concentration, 5%. Here, let me start with this one. Here, the EPR spectrum and NMR intensity as a result of dynamic nuclear polarization matches very well. However, in this particular case for a silicon 1% sample, here's the EPR transition, and NMR intensity peak is shifted outward from the EPR transition. Let me tell you why. Remember, in the mechanism side of solid effect, I said I excite either flip-flip or flip-flop transition. In this 1% 29 silicon sample, the EPR line shape, this blue line shape, is so sharp, line width is so sharp, that now EPR line is situating somewhere around here, and then flip-flop transition, flip-flip transition, and flip-flop transition is situating outside of this line width. Okay? So this is why. So we have been able to resolve flip-flip, allowed transition, and flip-flop transition thanks to isotopic purification. By reducing 29 silicon, we were able to sharpen the EPR line so that now we can see this part is actually flip-flip transition. This is flip-flop transition. Unfortunately, in EPR, the actual flip-flip and flip-flop are not allowed. So it doesn't show an EPR spectrum. But the transition is there. That's why the NMR enhancement is strongest just outside, and this point are flip-flip and flip-flop. So we call this, this effect is known as a resolved solid effect, which has been observed for the first time in silicon. Okay? Temperature dependence. I show you EPR line intensity as a function of the temperature. Here's the temperature dependence of the EPR line intensity. In 5%, 10 to the 16 sample, phosphorus. This is a 5 natural silicon, 10 to the 17, more phosphorus, so it has only one EPR transition, and the temperature dependence looks very different. Now I'm going to change the horizontal axis. No, sorry, vertical axis. From EPR line intensity to NMR, 29 silicon NMR intensity. But you don't see any difference because this is NMR intensity, this is EPR intensity. It has exactly the same temperature dependencies. Okay? So why is NMR intensity low in temperature below 10 Kelvin? At such low temperature, phosphorus electron relaxation time becomes very long. Remember, we had two levels. We excite electrons to the top level, and then these electrons have to relax to a certain level. This relaxation does not occur at low temperature. That's why we don't get 29 silicon orientation at such low temperature. At high temperature, phosphorus electron bound to phosphorus are ionized or otherwise detached from phosphorus. So if we lose the electron, then there's no electron paramagnetic resonance either. So this is why at high temperature, we don't get any EPR transition nor DNP, 29 silicon NMR intensity. Okay? However, for a high phosphorus concentration, the trend is different because even at low temperature, we get certain relaxation. So that's understood as far as the generation part is understood. So now I move on to the spin diffusion part. Here I show you the 29 silicon NMR line shape. 1% sample, 29 silicon 1%, 29 silicon 5%, 29 silicon 10%, and so on. Before I go into the discussion of the structures, let me just remind you that without microwave irradiation, the 29 silicon peak is like this. So you practically observe no 29 silicon nuclear NMR peak without microwave radiation in EPR machine. But with excitation in EPR machine, we see strong 29 silicon nuclear polarization. That means microwave indeed oriented 29 silicon. Okay? And the line width comes from the interaction between 29 nuclear spins. It's the dipolar interactions. So the line width is basically related to dipolar interaction strength between neighboring 29 nuclear spins. And this dipolar interaction is also responsible for nuclear spin diffusion. So from the width, we can estimate the nuclear spin diffusion coefficient. So basically, we just measure the width. And that's NMR line width for different 29 silicon concentration from 1% to almost 100% is plotted here. And it has two shapes. two dependencies. These are experimentally found line width. And this is in accordance with the theory published in this PhysRep B. And at low concentration, the line width is supposedly proportional to the concentration. That's why it's proportional. At high concentration, the line width is supposedly proportional to square root of concentration. And that's why we had second regime. Okay? And transition from here to there is supposedly continuous. So, and this is just a black line. It agrees very well with our experimental observation. So that's the line width. And from this line width, we can estimate the diffusion coefficient, spin diffusion coefficient, which is shown here. So diffusion coefficient is in the range of 10 to the minus 14 square centimeter per second as a function of the 29 silicon concentration. 29 silicon concentration gives average distance between 29 silicon nuclear spins. And then that grows like this. And there was also theory by Nolden et al. How such diffusion should occur. The dependency is not exactly same as what we found, but roughly the same. So I think qualitatively, we have also been able to confirm his theory. So now let me show you the effect of crystal composition. Okay, here's a different 29 silicon concentration. Here's a phosphorus concentration is not shown anymore. Okay, and then this is a DNP mechanism. This is a resolved solid effect, 1%. This is differential solid effect. This is the Overhauser effect, and so on. Diffusion hour is given here, and then enhancement is given here. The 29 nuclear spin enhancement is here, and finally the polarization is given here. So the maximum polarization we have been obtained, polarization of 29 silicon we have been obtained, is 1.45%. This is more than 1,000 times better than thermal equilibrium. So we've done quite well. But we want to go up to 5% to realize quantum computation. How can we increase this? First of all, if we can increase the power of the microwave, we should be able to increase this value. Also, if we can increase the magnetic field, so irradiated frequency during saturation, we should be able to increase this. But I guess the bottom line is that by performing studies using different isotopic compositions and also different phosphorus concentration, we have been able to identify dynamic nuclear polarization mechanism of 29 silicon using electron bound to phosphorus. Okay. Also Hiroshi did, what Hiroshi did is that he also tried to study the effect of band edge gap illumination, effect of light illumination which has energy larger than band gap of silicon. And he was able to increase but with 400 milliwatts or 700 milliwatts irradiation, he was able to increase the polarization at this low temperature regime where I said it's a relaxation limited, but not as high as what he obtained in dark. Okay, and this is a summary. So you can read the summary. We should be able to increase this even higher with using higher microwave power or higher magnetic field. So thank you.